So what we can see is that in terms of the ratio of the spring constant due to residual stress to the geometric spring constant, well, the, the length over the beam width squared appears in there. So if we have a long beam that's slender, then residual stress is more important. A beam that's shorter or thicker will be less sensitive to residual stress, right? And it's really the ratio of the residual stress divided by the Young's modulus of the material that matters. So if we have a material like oxide, for example, the Young's modulus is about 69 gigapascals. So then residual stress obviously is going to be more important than if we have a material like, for example, diamond, where the elastic modulus or Young's modulus is about 800 to 1,000 megapascals. Okay, and so in what follows, I'm going to actually do an analysis where we calculate the spring constant just due to residual stress. And so what we'll see is basically we're going to be looking at so more or less what I'm going to say is sigma naught is important if sigma naught is large relative to E times H over L squared, right? Because if, let's say, for example, sigma naught is equal to E times H over L squared, then this thing will be this thing will be 3, okay, right? K sigma would be 3 times the geometric swing constant. Okay? So let's do an example. So this is a relatively an older accelerometer. I'm actually not sure whether analog, this is from Analog Devices. You can see the label here. This is an SEM image of their accelerometer, an ADXL50. So this is a one-axis accelerometer. The 50 part, I think, actually I don't remember whether this is a 5G or a 50G accelerometer. That's what the 50 stands for. And so you can see there's these capacitive plates here. These are for the capacitive sensing. I will have a lecture about that. And here's the springs, the flexures. And so these points here are the anchors. There's basically a spring at the top and a spring at the bottom. And this is the proof mass part in between. And the anchors here are on the ends. And you can see here this is the date on the date on the SEM is January 1994. So this is actually a 20-year-old SEM. It's an old image. The newer Analog Devices accelerometers don't quite look like this, but anyway, it's a good example. So here, what we're using is now we're calculating the in-plane stiffness, and so the dimension that I said that was into the page, I called that B. Here, I'm going to use W, I use B. Okay, so B is the thickness of the film, right? Because remember, we're talking about bending the beam. So like here's the anchor like this. And so we're talking about in-plane deflections like this. And so this feature here is the width drawn on the mask. Right, so here's the force that's applied to this beam. So the H is the line width on the mask, and the B, the z-axis dimension, is the thickness of the polysilicon. And so for these suspension beams, what we're going to do is we're going to treat them. Let's see, I guess it says here, the length of this part here is 260 microns. You can see this is a scale bar that's 100 microns long. So this part here is 260 microns. They are 2.3 microns wide, and the film thickness is 2 microns. So it's 2 micron thick polysilicon. And it says the average residual stress in this device, sigma R, is 50 megapascals. Okay? So now let's calculate for this device whether the residual stress is important. So it says the mass of this structure is 220 nanograms. 60% is from the capacitive sense fingers. So this is 220 times 10 to the minus 9 grams, which we could write as 220 times 10 to the minus 12 kilograms. You know, when we're calculating forces, for example, we want to use kilograms as the units, right? Because we end up with newtons being kilogram meter per second squared. So it's 220 times 10 to the minus 12. So we're not going to use that here, but later on, if we wanted to calculate the natural frequency, which I may do on one of these slides, then we're going to use this as the mass, 220 times 10 to the minus 12. That's the kilograms of the units. And for the suspension, we're going to approximate it as two clamp beams with the length equal to 2 times the length of the individual flexures, 520 microns. And so what we're saying is if we go back to like the very first, I'll have to jump back to, yeah, so if we look at, remember this is the, we started from this point of view, this is the beam of length L, and we are talking about a point force applied at the center of the beam. And so really for this analog devices accelerometer, that's a pretty good model, because if you look at it, sorry, I have to sort of flip through things, right? We can see it's clamped here, and really we could think about this as being a point force, and so that it doesn't really matter that, that this takes up some length here. We're just going to treat this as one continuous beam. So each beam is 520 microns long, and let's calculate what the spring constant should be. First thing is to see whether the residual stress is significant, okay? And so I said what I was going to do is I'm going to compare sigma naught to E times H over L squared, and so that is just like it says above. The elastic modulus for the poly is 150 gigapascals, and we have 2.3 micron width on the mask, and it's 520 microns long. And so when we calculate that, we get 2.9 megapascals. And we know that sigma naught, it was given, is 50 megapascals. And so sigma naught is much bigger than E times H over L squared. And so residual stress is important. It's actually going to give us, it's actually going to be the dominant source of stiffness in this device. So the bending contribution, if we look at the previous calculations, we'd get that this is sort of the geometric is what I would call it. So maybe let's call it K geometric. So if we just think of a stress-free beam, this is the stress. This is the spring constant we get. It's pi to the 4th over 6 times EBH cubed over L cubed, and that's equal to 0.8 newtons per meter when we plug in all the dimensions and the Young's modulus. And from residual stress, K sigma is equal to 2 times pi squared over 2 times sigma naught BH over L. And so we get 4.4 newtons per meter. So wow, the spring constant due to the residual stress is really the dominant thing. And so the total spring constant, K total, is the sum of those two guys. It ends up being 5.2 newtons per meter. Okay, and I'll comment that this factor of 2 here is we're counting both springs. So this is due to the 2 springs. Okay, and really for this device, we should really think about this is almost more like a string in tension. Strings have no stiffness on their own, right? So there's no geometric stiffness to a string. We all know this because you can dangle the string from your hand and it doesn't have any stiffness. It's only when it's under tension that we get stiffness. And so this part here is that tensile stiffness component of it, and it's the dominant part of the stiffness in this device. The other thing I'll comment is that you can, like this geometric spring constant, if you went back to the previous lecture where I talked about flexures, we had a formula for a clamp beam, and it didn't have this pi to the 4th over 6 on it. It had some other constants. And so you can look at that formula and compare it to this, to what we got here for the K geometric. This part here comes from the particular trial function that we chose, right? So we got a pi term in there because we used a cosine as our function, right? We had like cosine pi x over L in there. And so when we do the calculations, these things come because of the trial function that we use. So this is not the exactly correct solution. It's not. It does not if you look at the analytical solution for this clamp beam, we get a slightly different answer. But I think what I would encourage you to do is to check it versus the formula on the table, and you'll see that this answer is pretty darn close. Okay. So, and if you used a different trial function, you'd get a different answer. But if you use a pretty good trial function, you get something that hopefully is very close to the real solution. And now, in terms of the resonant frequency, it's worth writing down here. So the natural frequency here is, we write it like basically 2 pi fn, right? So normally we would calculate, so we write omega n is square root of k over m, we would normally want this to be in units of hertz, right? So this is the natural frequency in radians per second, and this is in hertz. And so what we get is that Fn is going to be 1 over 2 pi times square root of 5.2 newtons per meter divided by, remember we got to use kilograms here, 10 to the minus 12 kilograms, because we're using newtons in the numerator. So we get 24.5 kilohertz. And the datasheet value is 24 kilohertz. So this is pretty good calculation. And so I just mentioned here, we've not included the frequency pulling effect of the DC bias voltage on the sense capacitors. So if you remember in our lecture about electrostatics, there is this Ke, electrostatic spring constant, and that's a negative number. It's less than 0. And so the real natural frequency, I'll write it as omega n here, is square root of the K that we found, which is, I call that KT, minus KE over M. And if we were to include this KE, that may be part of the reason why our calculated frequency is a little bit higher than the datasheet value. Okay, so that's all that I have on this material, and then I'll begin the lecture that talks about the Rayleigh-Ritz next.